In this video, let's draw the Lewis structure, then determine the molecular geometry and polarity of ammonia. I have other videos explaining covalent bonding, Lewis structures, and valence shell electron pair repulsion or VSEPR theory, so I'll refer you to those videos. In ammonia, we have one nitrogen atom and three hydrogen atoms. The first step to drawing the Lewis structure is to obtain the total valence electrons. There's a shortcut here, and the shortcut is to go to the family where that element is in and get that second number of the family, in this case 5 for nitrogen and 1 for hydrogen, and that will give us the valence electrons for those elements. So we have 1 nitrogen and we have 3 hydrogens. Nitrogen has 5 valence electrons, so this would be 5. Hydrogen has 1, and we have 3 hydrogens, so that'll be 3. And so the total valence electrons are 8. As I mentioned in a previous video, what we want to do with the Lewis structure is show how these atoms are connected, but more importantly, show the reader in 2 dimensions how these valence electrons are organized in that molecule. So the rule for Lewis structures is the least electronegative atom goes in the center. Electronegativity increases from left to right, but there is another rule here. Nitrogen is more electronegative than hydrogen. Hydrogen is the least electronegative. However, hydrogen, because it only has the 1s orbital, can only form the 1 bond, so hydrogens can never be in the center of a molecule. So right here, nitrogen would go in the center. And anywhere around the nitrogen, we'll draw the 3 hydrogen atoms. I'm not worried about geometry yet. I'll get to that in a moment. So just anywhere around here, I'll draw the 3 hydrogen atoms. And the next step for Lewis structures is we'll draw a connection here. So this is the bond between the atoms. Each covalent bond is a shared pair of electrons. So if you count with me, we have 1 pair, 2 pairs, and 3 pairs. That's 6 total valence electrons that are represented here. So out of the 8 total valence electrons, we've used 6 for these 3 bonds. Interestingly, there are 2 electrons remaining. Again, in Lewis structures, we want to show the reader where all 8 electrons are in this molecule. So 6 of them are participating in these 3 bonds. And then the other 2 will fill the octet rule from the outside going in. Now, the rule for hydrogen is the duet rule. It does not have 8 electrons around it. It can only have 2. So each hydrogen is participating in its own bond. But if you take a look at the nitrogen around it is sharing these 6 electrons. So to satisfy the octet rule, it's going to want 2 more. And so we'll draw a lone pair on that nitrogen. So there are the 2. And as I've mentioned before, this is the goal. When you're drawing Lewis structures, count the total valence electrons, and you want to end up with 0 here. In other words, when you show the reader the Lewis structure, you want to show them that 2-dimensional representation of the molecule, and you want to show all 8 electrons, so you want this count to be 0. Now, let's get the molecular geometry. This is a table that I use in my classes, and if you just go from left to right, you can get the molecular geometries, bond angles, and even hybridizations for these central atoms. In general chemistry, when you're dealing with small molecules, we usually just look at that one central atom. So the first thing I'll do here is just count the number of groups around the central atom. So groups are lone pairs plus atoms. Interestingly, around nitrogen, there are 4 groups. There are 3 atoms, and there's 1 lone pair. So the groups around nitrogen, 4. Each hydrogen is bonded by a pair of electrons, and then we have the lone pair. There are 4 groups. And from the table, you can see those 4 groups will give us that electron pair geometry. So there are 4 pairs of electrons here that are giving us some shape. And the electron pair geometry is coming from those electron pairs, bonding and non-bonding. And so those 4 pairs of electrons give us the tetrahedral shape. Next, the molecular geometry is dependent on the number of bonds and lone pairs present. In this example, around the nitrogen, there are 3 bonds and 1 lone pair. So going to the table, we can follow this line right here for 3 bonds and 1 lone pair. And that's going to give us a shape or molecular geometry of trigonal pyramidal. Some textbooks will call this trigonal pyramid, trigonal pyramidal. Sometimes I've seen textbooks write pyramidal and that's it. The bond angle, about 107 degrees. Now, tetrahedrals will have a 109.5 degree bond angle, but because of that lone pair takes up some space, so that's going to squeeze the angles just a little bit here. So we're going to call this 107 degrees. For the hybridization around the central atom, I have another lecture on hybridization where I go into more detail. Just to summarize here, these 4 pairs of electrons around the central atom, that's giving us that tetrahedral shape, those 4 pairs are going to sit in hybrid orbitals. And so you want to have 4 hybrid orbitals, 1 from the s, 3 from the p, and so that gives us our 4 mixed orbitals for bonding. So we'll call this sp3 on the central atom. Before we get to the polarity, let's take a look at the ball and stick model. In your molecular models kit, you'll usually see nitrogen as the blue atom, and it'll usually have 3 holes. Sometimes because of the tetrahedral electron pair, you can use the one with 4 holes. That should be okay. Hydrogens are usually white atoms. And so here's my trigonal pyramidal. The white is a little hard to see here on the white background. So what I'm going to do is I'm going to change those colors. Let's go ahead and change those colors so we can see them a little bit better. So I'm using red, green, and yellow. And so here you go. Here's what your trigonal pyramidal looks like. Perspective is very important. If you have this bird's eye view here, this might look like a triangle, but if I move this over to the side view, you can definitely see this looks like a little umbrella here. And so this is where you get your pyramidal shape. If I wanted to draw the wedge and dash sketch, I'll go ahead and hold it this way. So there's a bond here that's in the plane. So I'll go ahead and label this 3D. So here's my nitrogen. There's a bond here in the plane. So there's a line here going out to a hydrogen. But interestingly, right here, you see this red atom is actually pointing towards you. There's a green atom pointing away from you. If I hold it this way, that green atom is hiding behind that red atom. So I'll tilt it just a little bit so we can see what's behind that red atom. And so for the atom that's pointing towards you, this red atom will draw a wedge. And for the atom that's pointing away from you, that green atom will draw that in dashes. And let's not forget, we still have that lone pair of electrons that's sitting on top of that nitrogen atom. You can almost imagine if there's a lone pair up here, it's sitting in that hybrid orbital, but taking up a little bit more space. So that's why the bond angle gets just a little sharper there at 107 instead of the 109.5. So let's close this up by talking about the polarity. To understand the polarity, the molecular polarity, we need to understand the individual bonds in here. What are the individual dipoles telling us? We have three NH bonds. Nitrogen is more electronegative than hydrogen. So when you look at the bonds, this nitrogen is actually pulling this pair of electrons towards it. So there's a dipole right through here. Same thing here with this atom that's pointing towards you. This bond right here is being pulled towards the nitrogen. And this hydrogen's pointing away from you. This bond right here is being pulled towards the nitrogen. So you see the electron density being pulled upwards towards the nitrogen. Let's bring that model back. And so this is interesting. You can see the three bonds here, and the electron density is actually being pulled upwards towards the nitrogen. What I like to tell my students here is to look at these dipoles. There is no dipole pointing towards this dipole to cancel it. There's no dipole pointing towards this dipole to cancel it. So all the dipoles are pointing in that one general direction. So that's going to make this molecule asymmetric. And asymmetric means a polar molecule. So these dipoles act as vectors. We can add up these vectors, and for the molecule, you're going to have one big dipole going right through the center here. And that's our molecular dipole.